Okay, so good morning. This is lecture 12 for our course, and so today, in the next few lectures, we continue our study into magnetic properties of matter. Okay, and so this will take some while, and so we will see an example. Okay, where we will see the first example of a phase transition. Okay, so but the solution will be approximate. Okay, so the conclusions will also be approximately right. Okay, so but there'll be general theorems, etc., which will tell you, where it is wrong and stuff like that. Okay, so this is the thing, and so what we want to do is we'll start with the model. Okay, so what we will do is we will think of magnetic dipoles on a lattice. Okay, so what I have in mind is if it's 1D, if it is one dimensional, this thing we call it chain or something. So there'll be a bunch of points with sides, So there'll be some equal spacing, whatever. So this is your lattice in one dimension. This would be a canonical example. 2 dimensions, we will have, for instance, we could have a square lattice. Okay, this can have infinite extent. So what is the idea here is that there will be dipoles which can orient in any direction, so something like this. Similarly here. So on, so forth. You get the idea, right? It could even go out of plane because it's some 3-dimensional thing.
So these dipoles are the electronic dipoles.
Magnetic dipoles. Okay, something like this. Okay. There can be other lattices, etc. But so this is the picture that we have, and so the idea is that so we already know one Hamiltonian. So we have already seen a coupling to an external magnetic field. Right, of the form okay, so this is just sum over I, which is like run over all spins. So here it will be over the lattice of something which we'll write like this, mu dot b. Right, we have seen this. Okay, and we even computed the partition function and we saw that, okay. So, but the thing is that this Hamiltonian cannot explain, for instance, ferromagnetism and things like that. So we will need something more. So we'll modify this. Okay, so we'll write H equal to, we'll add an extra term, and that will be an interaction, okay, between nearest neighbors. Okay, so if you look here, so nearest neighbors means, so if you pick here, if you pick a site, let's mark nearest neighbors of something. Okay, so let's say we pick this site, and this will be its nearest neighbors, right? So they're next to each other, but next to nearest would be 2 away, but they won't. So we'll put interactions of this kind. So if you pick this guy, the nearest neighbors are this, and this, and we'll talk about coordination number. That means the number of nearest neighbors. So in one dimension it's 2. On a square lattice it is how many? 4. Okay. So let's get back to this thing. So we'll write something like this, minus, this is not the most general thing, but I'll just write something. Okay. Does anyone know what this symbol square bracket ij mean? Nearest neighbors. Some overall nearest neighbors. Okay. Is this clear? Okay. So this is what this thing would be. And so this is the Hamiltonian that we will consider. And so you can see that this is different from the earlier one because there are nearest neighbor interactions. Okay, so let's look at this same into. So we have this Hamiltonian, and let's consider. Okay. Before that, let me.
Capital J constant.
Huh?
What is capital J?
J is just some constant. Okay, like B also is some vector like constant, right? It's some external thing. Okay, so J is some coupling, and I've taken it to be the same for everything. Okay, and before that, I just want to say one more thing before I. So we'll study this a little bit more. So what we will do is recall that if let's assume that this comes from spin, and then what we will see is that mu would be G times, we had worked out this thing for a particle, right? Q, I'll write something here, H bar by 2n times spin by H bar. So here we have already seen this, but I'm multiplying and dividing by H bar. So this makes this, since S is measured in units of H bar, okay, so the spin, usual quantization conditions, etc. So this will just take care of that. So this is dimensionless. So we get something which has a dimension. This has, what do you call the, so this, and if Q is the electric charge, then we have something called mu B, which is called, which is H bar by 2nc, which is called, which has a name. Just 1 second. நீங்க என்ன இல்ல சார் நீங்க இப்படி தூக்கி போட்டுட்டு மோசமா இருக்கு நீங்க போட்டோ எடுத்து போனா லெட்டரா இல்ல அது எடுத்து அது வாங்கி இல்ல சிமெண்ட் இல்ல அதான் எடுத்தாங்க நான் நீங்க எடுத்து நாங்க தான் எடுத்தோம் அம்மா ப்ளீஸ் அம்மா தெரிஞ்சுக்கம்மா இந்த கிளாஸ் நடக்குது I'm sorry I got interrupted. Yeah. So have you seen this quantity anywhere? Yeah, it's called the Bohr magneton, and this is in SI units. And in Gaussian units, mu b, will there be a factor of C? Okay, so usually mu is measured in terms of Bohr magnetons, and so it's and you put a G factor. So we can absorb. Let me make this into E. Okay, so this is called the Bohr magneton. So now coming back to our Hamiltonian. Okay, so we'll first consider the situation when B is 0. Okay, so there's only nearest neighbor interactions. Okay, so consider the case when B is 0. Okay, so then the Hamiltonian is just minus J summation nearest neighbor mu I dot mu J. Okay, so this is what we get. And so now there are two cases to consider. J greater than 0 and J less than 0. So let's look at this situation and ask what is the ground state. So if J is positive, so think about this, mu I and mu J are two vectors that can rotate in, they can be taken arbitrary values. So let's say mu I is fixed, and so what is the maximum value that you can get from mu I dot mu J? When does that happen in terms of the angle? Okay, when they are parallel. Okay, so when they are parallel, and if they are anti-parallel, you will get the lowest, and it will be a negative of the other thing. Okay, so but if J is positive, Hamiltonian, when does it take the lowest value? Yes, Rajesh, louder. All are aligned, right? They are all parallel. Okay, so ground state. All spins are aligned. Okay, and what about J less than 0?
Anti-aligned.
Okay, so when nearest neighbors but there is a subtlety that there exist situations where you cannot make a configuration where so you could have a problem where you will have what is called as frustration. So in a square lattice, this we are done. Okay, so let's stick to that. I won't discuss here. I think so. But now I have a question to you. The ground state is all the spins are aligned, but which direction?
It doesn't matter.
Okay, so all directions. So okay, so there is a degeneracy which is given by the all possible directions. What about here? Let's say there is no obstruction to doing this. You can always do that. Again, what is there a degeneracy for J less than 0?
Yes, sir, but depends on the middle one.
Yeah, you fix one and then you're able to assign it everywhere. So again, same. Again, there is a degeneracy. Okay, so that's what we get. And these two have names. So if these are all aligned, you'll see that there is a overall macroscopic magnetic moment, right? That's what this means. And that is what, and there's no external magnetic field. So what would you call this ground state?
So magnetized state.
Yeah, so it's a ferromagnetic. So we call it the ferromagnetic coupling, ferromagnetic state. Okay. So here, of course, total magnetization in the J less than 0 case will be 0, but we can have something like a twisting where we take opposite sums, and you can get something. So this is anti-ferromagnetic. Okay. So I'll just make a remark on some lattices. It is not possible to define an anti-ferromagnetic ground state. So how would we start? You will pick one side and say that has to be aligned in some way. You fix that. Okay, that's arbitrary. Now that takes care of the degeneracy. So then you look at all its nearest neighbors. Okay, and then you make them have opposite anti-aligned. So you would think you're done, but it could be that in that lattice, two of those guys, which is the nearest neighbor of your atom, they are also nearest neighbors to each other, but then they will be parallel. Okay, so this is called these systems there is frustration, which is the inability to assign, unique values to get a ground state. Okay, so I'll just give you a toy picture. I'm not giving a lattice or anything, but so let's say that we have a triangle. We have spins here. One, 2, and 3, and let's say the Hamiltonian is just this way. It's just the is ferromagnetic coupling. I don't want that. So yeah, go back to this. So you can see that I can do the following thing. I can let me actually get rid of this. So I want to assign things the spins. So I do this. So 1 and 2 are antiferromagnetic aligned. But now what do we do here? Do you see the issue? For site 3, they're all nearest neighbors. So if you give me site 1 and then I assign 2 and 3 will be up, but then 2, 3 will be parallel. If you start from 2, then the other one will come. Okay? Yes, Siddharth? Okay.
So this problem will come only when it is not an one-dimensional lattice.
Oh yeah, yes, yeah. In 2D, yes. 2D, 3D and things like that, you can have situations like this. Okay? So this is an example of frustrated. Okay? So, but, this might look, this is a bad problem. No, it's not actually. It's a very, very interesting problem. And if you go and look for frustrated magnets, you will see that it's a very, very active area of research. And especially once you go to quantum mechanics, the quantum mechanical ground state could be linear superpositions of these things. Okay, so asking what is the true ground state, etc., is actually an active area of research. So this is not, even there are conferences. Even IIT Madras had a conference a couple of years ago on frustrated magnetism. Okay, so this is actually very, very interesting from a physics viewpoint. But so I just want to come back to this Hamiltonian. So what we will do in the rest of the lecture, we will assume a ferromagnetic interaction, which means J is positive. Okay, for the rest of the lecture, that's what we will do. Is this clear? Somebody? Huh? Okay, good. So assume J is greater than 0, that is the interaction is ferromagnetic. Okay, so this model, so this is this model is, I guess, called the Heisenberg ferromagnet. Okay, and if you choose the other spin, you get Heisenberg antiferromagnet. Okay, but this problem is too complicated to solve. So we will solve an easier version. We will attempt to solve. An easier version, easier version, that is anisotropic. Okay, in other words, the ferromagnetic coupling involves only one of these things. Say mu z, sz, or equivalently mu z. Okay, so what we will do is so mu z will be j mu b times sz by h bar. Okay, so we are focusing on only the interactions are happening. So there is some reason there is an anisotropy in the problem, and so we're going to do this. And let me simplify things, and let us denote Sz by h by the symbol sigma. Okay, and absorb factors like g square mu b square into the definition of g of j. Okay, so this Hamiltonian, this new Hamiltonian, I will write out now. I'll use the same symbol j, but j is actually not that. It is j minus j, nearest neighbor ij, sigma I sigma j. Okay, minus magnetic field. So we'll just call that sigma sum over I, sigma I, and now it should couple to that. So we'll just write some sigma I times b. Okay, and we'll assume that the b is homogeneous, so it's same for all. Okay, is this fine? So this is our simplified Hamiltonian. Okay, and if spin is half, then let's work with then sigma will take values plus or minus half. Okay, So that's what will happen. So I actually simplify things. So let's rescale. So instead of writing plus or minus half, I will write plus or minus 1. Or should I? No, let's leave it. Let's leave it as plus or minus half. Okay, good. Okay, so is this clear? So we get a new Hamiltonian where the sigma can take only two values, which I'm taking them to be plus or minus half. Okay, so this Hamiltonian has a name. Does anybody know the name? Okay, so it's called the Ising model. Okay, but Ising was German, so in German it's Ising. Okay, but this was a problem given by his advisor, whose name again you will know. His name is Lenz, so it should actually be called the Lenz-Ising model. And this was Ising solved this model exactly, I believe, in his PhD thesis. Okay, and he wrote only one paper in his whole life, and that was this model. But he is very, very famous because of writing a paper which has made a huge impact. Okay, so this is the model which we are going to study. Okay, so the Lenz-Ising model. Okay, so if you see somebody calling it Ising model, that's okay, because it's just what I'm calling Lenz-Ising model is more or less universally accepted as Lenz-Ising model, but we should give credit to Lenz who actually gave this problem. Okay, so except now this is like so textbook that it will be a problem for our course. Okay, so I'll pause here, and so our goal is to compute what is the magnetization. So what is our goal? Okay, assume that the system is in contact with the heat path at temperature. Okay, and what is it we would like? We would like to compute the magnetization as a function of temperature and V. This is our goal. Okay, so now what is the microscopic definition of magnetization? So it should be right, each of the guys, their individual moments, and whatever that value mu I takes, that's what. Remember, mu I is the z value. This is what is called the magnetization, but we should work out what is the expectation. Okay. Okay. But what is mu I? Mu I is proportional to, up to some factors, is g times. Okay, so what we will do is I might be Cavalier, and or maybe I won't be Cavalier. I'll just call this object. I'll call this M, this small case M. No, I don't want to do that. Okay, so so you can see that this is a constant factor. So we might even all I want to say is that I might I don't promise, but I might refer to this as magnetization. Okay, but that is loose. So So I'm just protecting my back and saying this, but really we have to have this g times mu b. Okay, so this is what we would like to compute. So now comes the question: how do we compute? So this is. So what is it I should do? This is a statistical mechanical problem. You're given the Hamiltonian. You're told it's in contact with the heat path. So what is the first thing that we have to compute?
Like the partition function.
Canonical partition functions, right? So we should do that. So Z will be sum over all possible values of sigma I, okay, times e power minus beta times h, where h is whatever I wrote. So let me just write it once more quickly. Okay, so when j was 0, we have done this computation, right? Little z, there is no interaction term, so I can just write it as little z power n, where n is the number of sides. And what would little z be in that case? Z would be what would z be?
E power minus beta sigma.
Sum over z. Right? And so this is some cos hyperbolic. Correct? This is what we know. But what is it we want to do? We want to compute. We want to compute it this way, but the interaction implies that we cannot, that z is not little z power n. Right? You pick a site. If you pick a site I, there are terms where you can't carry out just the sum over sigma j's. You can't do that because you have to. So because of this term, you can't do it. Okay. So you can't do it. I mean, if you don't understand, think about this. Think about this if you don't get it. Okay. But whenever there are interactions, that's not true. So we need to compute z in a different way. So I'll make a remark, okay, that there exist exact solutions for t equal to 1 and 2 with b equal to 0, and I believe, and d equal to 1 with b not equal to 0. So this is okay, and we will see at least d equal to 1. We'll see the exact solution, but these are solution is due to Lars Onsager, who won a Nobel Prize effectively for doing this, and is very is complicated. and out of it for our course. So I have given lectures on this for advanced statistical physics, but those require about 3 to 4 hours of lectures, and it's really fancy stuff. Okay. Very impressive, and okay, so it's useful that we know. So we will, however, solve it approximately using a method called mean field theory. Okay, so what I'll do is I'll illustrate it for the case of 2D, but 2D square lattice, but for 1D, or I mean the dimension won't matter, you'll see in a moment. So let's pick one guy, and let me indicate these are the nearest neighbors on a circular lattice, on a sorry, square lattice, not circular lattice. I don't know what circular lattice means. Okay, so these are the nearest neighbors. Okay, so we want to, so what we will do is, so if you call this guy, so what we have is couplings of if this is I, then sigma I, we have terms like this. There are 4 terms. For fixed I. Okay, I've just written those 4 neighbors. So the J label is just the nearest neighbors. Okay, so we just call these 1, 2, 3, 4. Okay, so that's what I mean. So we have this, and this is the problem. So what we will do here is we will replace sigma j by its mean value. We don't know what that is, but whatever that is, we will just say that on an average, so the picture we have is I'm focusing on the ith guy, and all the other guys, everything is fluctuating, but I'm focusing on the ith guy. And so its neighbors are all fluctuating. And so first approximation will say that it sees whatever is the average value. Okay, whatever that means. Okay, and so let us further homogeneity. There's nothing special about this thing. Homogeneity, we'll put that also, implies that sigma j is independent of j. It doesn't matter where you are on the lattice, the mean value will be the same. And so we'll call this, so we'll just call this, we'll call that value m. Okay, is this clear what we are doing? So we will let, the only thing we will let take the 2 values is the ith guy which we are focusing on. And then when you're working out that term, we will just write it in this fashion. Okay? Is this clear? So now what we get is something interesting. So we'll get with this approximation, okay, we get an effective Hamiltonian. Okay, which takes the form H effective equal to sum A minus J, okay, M, okay, and let me put some what should I call X. Usually coordination number Z is used. I don't want to use Z, so I'll just write some Y times minus Okay, because there'll be so many, as many y's, as many m's as this thing. You might wonder, should it be y by 2? I mean, for whatever physics that we have, it doesn't matter. Okay, so is this clear? So now I can rewrite this in a nice way. Okay, so this now looks like the case when j was 0, but that's a b effective, but where the j interaction term is going there and modifying the applied b as some b effective. Is this clear? Okay, so we'll do a computation of this, but this we know how to do. Now it has come back to the origin. This example, now it looks like this with b replaced by b effective. So I can write what is z, right? Now, oh, I made a mistake here. No, I'm fine. What is it? B effective upon 2, right? Okay, but we don't know m. I mean, but we don't know m. But we can compute it. So let us compute. What is m? N times n. So what? Okay, is the n times m times g mu b, right? Is the magnetization. Okay, so what is it we can do? So let us compute that. We can compute that. So we want to compute m. That would be equal to uh, g times mu b. Okay, and I can write an n times expectation value of sigma. Okay, so we need to compute this. So question is, how do we compute? How does one compute? We just need to do it for one I and put an n in front. So without worry. So we have done this, right? We have done this before, right? Do you remember what was the answer? Okay, so this should be summation. Okay, so we can do this. So it will be 1 by, let's just do it as little z. Sigma I equal to plus or minus half times the probability of that, that is e power minus beta b effective of sigma I, right? This is what we have, times sigma I here, the value of sigma. Okay, so this is equal to 1 by z, which is 2 cos hyperbolic beta b effective by 2 times sigma can take plus or minus half, so it is minus when it is plus half, it is this is okay. Did I get the sign right? When sigma I is plus half, sorry, minus, so this is a mistake which even people did earlier. So okay, so you can see that this is for up to this half, it is okay. So is this clear? Okay, so but what is sigma I? That is m. Okay, so we get an equation which is m equal to half tan a hyperbolic half into b effective, which was b plus, what was it? B effective was b plus jmy. So this is a transcendental equation for what variable? What is it we don't know and would like to know? N. Okay, so next lecture, that is tomorrow. So it's hard, it looks like it's very hard to solve. We will solve this graphically. Okay, so you can, what you can do is you can plot both left hand side and right hand side and ask where they will meet. So as a function of m. M equal, okay, so one is nothing, so one of them will be a straight line, the other will be something like this, right? So other one is, it goes, so let's do the case when b is 0, so it will pass through the origin. So you will have these two, and so you have to ask where will these two intersect? Okay, so these two pictures, we'll put them on top of each other. So it is m versus m on this side, and this is this whatever it is, the tan hyperbolic versus m. Okay, so we'll plot these two functions on the same graph, and wherever they intersect, it will give you the number of solutions, and you will see that the number of solutions depend. I forgot a beta here. So okay, so number of solutions will actually depend on temperature. It will also depend on V. Okay, so we will see how those things change. So I'll stop here and pause for questions.